this lecture is, we called it What Could Possibly Go Wrong? And some of you have been kind of noticing, just zoom in on this, I'm not going to write on this page because that's for later, but so we've got some rules that say how to evaluate lambda expressions, and the rules say things like, this one that says, well, if both sides of a plus evaluate to numbers, then the whole thing evaluates to the sum of those numbers. So we're basically saying how things work when stuff is as it should be, but my question to you is, what could possibly go wrong? Can we think of expressions which would not be given values by these rules? I mean, yeah, so, yeah. Is it the case that every program we can write in the grammar makes sense according to these rules? Or are there stupid programs that don't get values? Or are there sensible programs that don't get values and there's something wrong with the rules? See, these are the things we need to think about. Like, let's take that plus rule. What could possibly go wrong? I mean, do the expressions either side of the plus sign really have to evaluate to numbers? Nope. What else could they evaluate to?
String.
Well, we don't have strings in this language, but yeah, I mean, so if you've ever seen what happens in PHP, where they do have strings and numbers and stuff like that, what plus does when it gets random non-numerical things. But yeah, what are the non-numerical things that we happen to have? That, if it's not a number, what is it?
Store.
Well, so if it's not a number but it is a value, what is it? Yeah, it's a closure. Yeah, so it's got some store in it, and so we could evaluate S and end up with one of these things. I mean, what would happen if we were, foolish enough to write lambda x arrow x plus 2? What would that evaluate to according to the rules? Here are the rules. Well, the lambda term would evaluate to a closure, and 2 would evaluate to 2. Yeah, now I'm doing it. And then we'd get stuck because we wouldn't have a number here, so we wouldn't be able to apply this rule. So we wouldn't be able to get any further and actually say what the value of this expression is. So there's nothing. This, according to the rules, this doesn't evaluate to anything, which is probably just as well in some sense. I mean. So that's sort of one of the things.
So can I interrupt for a second?
So
wrong. Going back to the question about what judgments are, so there is no judgment with that term evaluating to something. So
but to be pedantic, there is such a judgment, but there's no derivation for it. In fact, one could even refute it. One could observe that, if anyone tells you, is it possible to derive this judgment? No. What's more, we can demonstrate that if these are the only ways to derive, as you could of course have an empty environment, you know, yeah, if these are the only ways to derive evaluation judgments, then not only is there no way to derive this judgment, but this judgment is demonstrably false. Right? So, right. What else can go wrong? It's fun. Is this, you know, one of the joys of being a programming language designer is to be a kind of criminal, right? You have to think, you know, let's take somebody's precious language design and shove it in a puddle and give it a good kicking, right? You know, how can we break it?
Or put in my own language, I've told you regularly that this is, most of this course is not creative because we give you things, you just follow the rules. And I'm always telling you, it's easy, just follow the rules. But actually, none of us like following the rules. We always like thinking about how to break the rules.
Yes.
So this is what we're doing now. How can we break these rules?
Yeah. So if we got something like, I don't know, x equals 5 and
Lower Connor.
f equals, maybe it's the empty environment, x, arrow, x. And then somebody gives us, I don't know, f applied to z. Is that going to evaluate to anything?
Come on, folks, you're very quiet. You're not quiet when I'm doing this.
Yeah.
There's no, I mean, I know he's a deity, but, you know, especially in the Protestant religions, you can talk to your gods. Sorry to bring religion into this corner.
Thanks for writing me. Glad I agreed today. Yeah. So, what goes wrong when we do this? Come on. Well, think about it, right? We're trying to evaluate an application. We better use the rule for application, which says we should evaluate the function. The function is a variable, so what does the variable rule say? Look it up in the environment. So everything's fine so far. Moving on to evaluating the argument, well, that's a variable. So what happens when we try and apply the variable rule? You know, what the hell is Z? So that's another kind of thing that can go wrong. So what we're saying is that the environment should give a value to all the free variables in the expression. The environment tells you what's in scope. And every time you write a lambda, you bring another variable into scope. So you should expect in anywhere you are in an expression, any variable you mention should either be bound by a lambda, an enclosing lambda, or it should be in the environment. Otherwise, you've got no chance of making sense of it. So that's another kind of thing that can go wrong. So yeah, I guess there's another thing that can go wrong.
Don't be shy. You're not shy.
I don't know if Neil has shown you this function.
I have. Using telepathy.
Yes.
Yeah.
That thing, yeah? You can see it's give me a variable and make it eat itself. It's a kind of auto-cannibalistic thing. And then we're interested in what that does. Well, what do you think it does? Does it have a value?
Have a guess.
I mean, delta has a value, but does delta delta have a value? Yeah, so what happens is that, you know, the application rule says, well, okay, you evaluate the function delta, you look up the, assuming, yes, I should put delta into the environment, of course, otherwise I make a scope error. Yeah, you evaluate the function, and that's fine. You evaluate the argument, that's fine. And then you try and evaluate what happens when you put the value of the value. So what happens is that the x gets bound in the environment to the value of delta, and then when you try and evaluate the body, you end up doing delta delta again. You end up back where you started, and so to get a value of the whole thing, you have to get a value of the same thing. So that's you're going to find that the tree that you build keeps on growing upwards with more and more layers and more inputs, and you'll never get to the point where you can produce an output. And you know, that's the corresponding to the situation where you know, if you ran the program, you would just sit there waiting forever for an answer. So that's another thing that can go wrong. Here's a slightly more subtle question. Let's again have delta in the environment. What would happen if I evaluated lambda x arrow 3 to delta delta? What do the rules say? What do you think the answer should be?
Depends on the order in which you evaluate.
It certainly is. So, if you were doing small step,
Well done.
if you were doing small step evaluation here, assuming that we substituted out the definition of delta, you would have a choice about whether to do the beta reduction of delta delta, which would get you back to where you started, but so you could keep on doing that forever, or you could do the outer beta reduction, where we substitute delta delta for every occurrence of x in 3, which would just give us 3. So in small step reduction, you have the situation where there is a way to get to a place where you're finished, but there is also a way to get stuck in a loop. You've got the small step reduction does not specify an evaluation order, and it's not the case that every strategy is bound to produce a result. According to these rules, we do have a fixed strategy for the order in which we evaluate things. So according to that strategy, what's going to happen? So it's all in the application rule. What do we store in environments? We store values in environments. And that means when we're setting up to do a function application, we need to get the value of the argument so that we can put that value in the environment when we're evaluating the body. And that means to do this application, we will need to get the value of delta delta, even though the function isn't going to use it. And that means we're screwed. So that's one of the things that happens with this call by value strategy. I mean, it's a design choice. Religious wars have been fought over it, where you know, should you evaluate the argument to a function before you start working on the body of the function? Well, if the body of the function uses the argument at least once, you're going to have to evaluate it. If it uses the argument more than once, then it's a win to have pre-cooked it. On the other hand, if the function doesn't use its argument at all, for whatever reason, then bothering to evaluate the argument up front is just a waste of talent and electricity. So there's an alternative possibility, which is, so I mean, this is kind of normal behavior. Most programming languages behave this way. You know, when you write an expression in Java, you call a method, you expect that the parameters to the method will be evaluated before the method call actually kicks in. That's just normal. So what we're saying is that the small step rules for the lambda calculus just, you know, it's anarchy, right? You've got, you know, you are free to choose an evaluation strategy. But when we try and do big step semantics, we usually end up making choices about evaluation strategy. And this one is called call by value because we say that variables stand for values, basically. That's what's happening here. And it has advantages, but one of its disadvantages is that we sometimes do extra work, which means things like this get us into trouble. So I think it's your go, Neil, for what we might do instead.
Right, so, yes, the lecture's called What Went Wrong? What Went Wrong? Even the title of the lecture went wrong. You can laugh now, it's okay. Laugh if you like.
Yeah, it was a genuine slip of the fingers. I decided to keep it.
So what Connor's showing you is that several things can go wrong. Ideally, you're writing your program, and you write great programs, and they all work. But, actually, that's not what happens in practice. You know as programmers, you can make mistakes in your program, and several things can go wrong. So what Connor pointed out was, first of all, there can be scope errors. So that means you need a value of a variable.
Slide it down.
Thanks. Well done. Train me.
Yeah.
You
Yes, don't write slide it down on your 1 minute paper. So.
You need a value for the variable, but the environment, or store environment, does not give you a value. By the way, all of these errors could be appearing in the current assessment. Does not give you a value. Okay, that could go wrong. We've seen that. We saw another one. So type errors. So the example here was lambda x arrow 5 plus 7. This is a type error because 7's a number, that's a type, and this is a function, that's another type. And you can't add functions to types. So that's what we're going to be doing in part 3 of the course. How to avoid these errors. I should say part of the goal of programming language designers is we accept that programmers can make errors, but we want to help them to avoid it. So we'll figure out ways to avoid this kind of error automatically. And then finally, programs may not terminate. And Connor gave you 2 examples. So his delta does not terminate. But also it's more subtle. It can depend upon the evaluation strategy. So that's the example lambda x dot 3 applied to delta. If you use call by value, where you have to evaluate this first, well, this doesn't terminate, so you don't get a value. So this does not terminate. In a value. Or call by name, where you don't evaluate this, you just say, oh, well, x is going to be this. Oh, I don't use x, I get 3. So there we do. Okay, so the reduction semantics we gave in the last lecture when you did applications, when you get this S, the first thing you do to S is you evaluate it. You try and get a value. So therefore this is called by value. Oops. This is a call by value semantics. Now, it's a nice semantics because we don't do substitution. Remember, we've also done a call by name and a call by value semantics where we have substitution in the rules. But here, there's no substitution, so that's really nice. But it's call by value. So the question for this lecture, or the question we're going to do now, is think about what happens if we want to avoid substitution. So we want to use environments, but we want to use a call by name semantics. So let's put this over here. And let's get another piece of scrap paper. So, question.
Done it.
Question. What does DOES? What does a call by name semantics look like with environments? Okay, so we're going to do this environment semantics because we don't want to write substitution, but we want to write it in call by name form. So the first thing we have to do, of course, is look at what are our values. That's, before we can say this is how you can get a value, you have to say what is a value. The first part is what is a value for this? And I'll remind you that when we did call by value, the values were, we had the value was either a number or it was an environment and then a variable RO a term. Okay? And of course, if that's what values are, I have to say what environments were. So environments were, well, they were either empty or there's an environment you've already built and then a variable equals a value. Okay, and this is why you see it's called by value, because the variables in your store are given values. They're not given arbitrary terms, they're only given values. So you couldn't put x equals 5 plus 2. That would not be an environment, because 5 plus 2 is not a value.
That's what forces us to evaluate stuff. We have to evaluate stuff before we can put it in an environment.
If you try to write an environment, and maybe you've done this in the hand-in, I can't remember, but I might have given you an environment where x equals 5 plus 2 and asked you, I claim this is a good environment. And you have to say whether it is or not. And if I had, well, the answer is no, it's not, because 5 plus 2 is not a value. Because remember, values are just numbers. All right. Okay. So So that's what we do with call by value. So what should we change in order to get the values for call by name? Okay. Now, I'm not a god, I'm not a deity, so you can talk to me. So let's start writing stuff out. Let's look at these values then. So we want to say the values are what? So we're just going to go through this and say, shall we keep this stuff or should we change this stuff? Do we need to change stuff here for a call by name semantics? So, what do you reckon? Are numbers okay as values here? What do you think? Are numbers okay? Will they be values? Is 5 a value? Or do you want to carry on working on it? Remember, values are things that we're going to stop working on because they're done. Is 5 done? Yeah, so numbers are fine. So we're going to keep numbers. Okay? Numbers are fine. No one's ever going to want to carry on evaluating a number. Okay, so that's okay. And I guess we can have a line. And now, previously, we said, well, we're not going to, value is going to be arbitrary functions, but we need an environment to keep them. So in this semantics, what should we do with functions? Should we keep those values?
Not sure.
Right, remember the point is that, where's it gone? No, sorry, it's up here. Previous page. I wrote it down. Yeah, so we want to keep all functions because all we're doing is in the store where it says an environment where we said x could be only values, so x could be 3 or 7, but it couldn't be a big program like 5 + 2. So that's the only change we're making. So what should we do here? Should we keep functions?
No.
Yes, because we're only
Well, we better change something about them, but we better have them.
Right. So remember, we're only changing the environment. So functions, we're not going to carry on working on functions. So we want to keep functions. So functions, we write var arrow term. But as Connor points out, the environments are going to change. That's the point about the call by name semantics. We're changing the environments, so the environments don't just have to have. See here, where's it gone? Where's it gone? Where's it gone? Here, the environment. When you want to extend a variable or give it a value, give it something, you have to give it a value. That's the only thing we're changing. We're trying to avoid this being a value. We're going to allow it to be an arbitrary thing, so we don't have to evaluate it. Of course, that has ramifications elsewhere. So, okay, so we'll have a new type of environment, and we're going to call it a thunk environment. That's a T.
Yeah.
So, new type of environment where, remember, it used to be an environment was essentially just a list of variables equals values, but now these variables don't just have to be values, they could be stuff which we can compute with. For call by value, environments were lists of variables and values, but now for call by name, environments will be lists of variables and further things to evaluate and further computations. So for example, we could say x is equal to delta delta. But putting it in the environment, we're not evaluating it because we may not need it. Okay, so let's have a look at what these environments will look like.
Can you keep that face for a second?
Ah,
Good. So it's worth looking at the call by value rules, that application rule. So the trouble with x equals delta delta is if you don't know what delta means.
Yeah.
Yeah. So I think if you look at the application rule for call by value and ask the question, suppose. Yeah. So here's where we have to do some work in order to put a value into the environment. Suppose you were a lazy bastard and didn't want to do any work. Unless you had to. What would you need to remember in order to do it later only if you had to? Would it be enough to remember S?
So that's really what we want to do. We don't want to evaluate S, we want to just stick S in the memory.
And hope that we don't ever have to bother with it. And then if we're unlucky, we'll have to evaluate it. But if we just remember the S, will life be good?
No.
Because there's no way we can actually ever get a value out of S unless we also remember the environment that explains the meaning of all of the three variables in S. Right? If we kind of lose that bit of information, we'll never be able to get our hands on the value of the thing. So we remember, it's like, memorizing a sentence for use later, and then when you use it later, you've forgotten what all the words mean. That happens a lot, actually.
So what we've just been saying is, if we want to put in our environments, not just x equals values, but x equals arbitrary computations, so there's one, or some arbitrary e, well, when we come to find out what x is, we'll need to know what the value of this is, or the value of this is, and these contain three variables. So that means we need to store the environment in which to evaluate e inside this environment. So now it's going to get more complex. The environment will be a list, and you'll get variables equals, and you can't just say a term. You need to say the environment for that term, because that term isn't a value. So this is the first ramification of what we're going to do. So, therefore, let's see, what is this part? So in the call by value semantics, see, a variable was equal to a value. But now we're going to put an arbitrary term here. But we can't just put a term there because we need an environment to evaluate that term in. So, just a couple of pages. Right. So, our definition for environments has to improve. First, change definition. So in other words, these new environments, which we call thunk environments, will be,
If you drop the square brackets, that's part of the closure notation.
a thunk environment is, well, we can still have the empty environment because of course the store can be empty. Or we've already got some thunk environment. And now we want to add a variable equals to something.
You've run out of
I
paper.
know, I know. And previously, remember, we just put a value here. But now we want to put a term with its environment. So we're going to have to put two things in there. So we're going to write for our two. It's not really the end of the lecture, is it?
10 minutes to go.
Right, so we're going to have to put the value of the environment, so that's going to be a term. So now a variable can be a term, but we also have to give it a thunk environment to evaluate that term. So here's the difference. There's the change. Previously it was var equals value, now it's thunk environment and a term.
Right, yeah. And this pair of a term and an environment to run it in, that's what's called a thunk. And thunk is a made-up silly word, a sort of bogus past tense of think. It's something you've thought of doing but haven't done yet. It's only been thought of. Well, I guess thunk is also what you get when you think too much.
Okay, so we've discussed what the values are. Tell you what values were, they involve thunk environments, and we tell you what thunk environments are. So now all we need to do is change the actual rules for these new environments.
We should at least manage to a good cliffhanger.
Okay, so these are our new environments, and these are the old rules, these are things we're going to have to change. So, how do I do this quickly, but give you the chance to shine. Right, so let's go through these rules quickly. So this one, if we're called by value, if this changes from an environment to a thunk environment, do we need to change the actual rule? What do you reckon? So if I've now got a thunk environment in which I evaluate n, what's the answer? What do you reckon?
Well, it stays the same.
Yeah,
Yeah.
it's just n. So, the environment's changed, they're more sophisticated, but I'm not using the environment. So nothing's changed. Great. Now let's look at another simple one, going up in complexity, addition. So now that's this one. What's going to change? So now I want to do gamma and s plus t. What's the rule for this? What do you reckon?
Stays the same.
Yeah, well, first of all, we have to evaluate s. So we'll do something like this. Does this change? That's a thunk environment, but no. I just need to evaluate s, get an m, evaluate t, get an n.
Yeah. If somebody wants to know the total, we're not going to get out of evaluating the pieces. There's no.
Sorry. Right. Okay, so that's so far so good. Not too much of a change. Now let's do the complex one, shall we?
Variables.
Variables. Variables. Okay, so this is the rule in call by value, which says if you want to know the value of a variable, well, look it up in the environment, and because this is only storing values, well, x gets a value, and you can return the value. Right. So, I guess it's your turn next. Will that change?
Yeah.
Yes. Brilliant. And why would it change?
Because it should require something else in the v's place.
Yeah, exactly.
Yeah.
Because
so when you look up the variable, it's not going to be a value.
Exactly. So gamma x equals, and now the environment says, I'm not going to get a value, I'm going to get a thunk. What letter did we use?
Yeah, I was using theta for thunk environments.
And is it E?
You've
T's?
been gammering away.
Yeah.
Don't worry about
At this
it.
point, is the variable this one used? This one. S. No?
I habitually call those things S.
Yes. Right. So there's our environment, and we want to work out the value of x. So there's our environment. It's got some definitions of variables, and then it's got the variable x is equal to this thunk, and then some more variables. And we want to find out the value of x.
Is that a gamma prime?
Yeah, that's a gamma prime.
Yeah, so that's just stuff before x. X is x and its thunk, stuff after x.
Now, previously we could just say, oh, what's x? Let's look at it in the environment, and we would have got a value. So you could pop the value down here. But now we don't have a value. We've got, well, x should be s evaluated in this environment. So what should we write to complete the rule? That's the intuition.
Would it be a thumb prime?
Well, so x should be whatever s is
Right.
inside this environment.
It's like we were hoping we were going to get away with not bothering to evaluate s, but shit, we've been caught out. Somebody wants to know what x is. We're going to have to do some work after all. What do we have to do? Though we have to
Okay.
evaluate s.
So how do you evaluate s then? How do you evaluate anything? We use an arrow. That's what we do for evaluation? Okay, go to the next. So, what goes on the left-hand side of the arrow?
We have to let them out soon.
Yes. So, we need to evaluate s, and what environment? It's s. We'll be finished in a moment. Your turn, coup de grace. Sorry, I don't know if you know French. The important bit at the end. So when we evaluate s in this environment, we're going to get some value. And then your turn, coup de grace. What's the overall answer?
The value?
Yeah. Oh, sorry.
Yeah.
So the moral of the story was previously, we did some work earlier, we evaluated s to some value. This is a value, we can just return the value. But now this is a term in the environment. We evaluate the term, and we get the environment, and then we can return the value. Okay, 1 minute papers. Thank you very much.
So the cliffhanger
Oh, sorry.
is, now that you know what the variable rule is, why don't you have a think about what the application rule should be?